Service friends, I am Orpheus Praxis, a researcher of the limits of formal systems and their applicability to reality, and welcome to my channel. Today, we will discover how cosmic acceleration can arise without any dark energy. Why should this model be regarded as a breakthrough in theoretical physics, quantum gravity, and cosmology? Because it unifies general relativity and quantum mechanics within the compact space S3. Ordinarily, quantizing general relativity leads to incompatibility between the continuum and the probabilistic nature of the wave function. The authors apply canonical quantization in the space RCS S3, where R represents time, global CMC synchronized. S3 is a compact, simply connected three-dimensional space with positive curvature. This allows for a discrete spectrum of geometric states, analogous to the energy levels of an atom, solving the problem of infinite density and avoiding singularity. For 100 years, canonical quantum gravity has failed to achieve precisely this: to find a space where quantum metric operators have a discrete spectrum without losing continuity. In this model, the acceleration of the universe emerges as a phase effect, rather than as a manifestation of energy. Instead of introducing dark energy or the cosmological constant, it is shown that acceleration is a geometric phase of the quantum state of the universe, an analog of the Berry phase. In other words, acceleration is an intrinsic property of the phase evolution of the metric, not a consequence of a new field or matter. Thus, Lil is not a physical force but a quantum phase shift. This is radical. For the first time in history, L receives an internal explanation within general relativity rather than being added from the outside. In this way, the cosmological constant problem is solved without fine-tuning. In classical cosmology, lambda is approximately 10 to the minus 52nd per square meter, far too small to originate from vacuum energy. Here, however, Lel does not exist as a parameter. Instead, the phase term delta θ reproduces the observed acceleration. No fitting, no dynamic dark energies, only a natural consequence of the quantum geometry of S3. This represents one of the deepest conceptual shifts in theoretical cosmology in recent decades. The authors introduce the phase law for cosmic acceleration. This is the key result. They show that the Hubble constant equals 1/3 of the rate of change of the overall spatial deformation in time. This means that the evolution of the universe is governed not by an equation of motion for matter, but by a law of phase evolution of the quantum state. This marks a step toward a wave cosmology, where space-time itself is a wave function. The model accurately reproduces the acceleration observed in SNIA and DESI data, the structure of the CMB, Planck, and it is consistent with the Friedmann equations for k equals +1. All this without dark energy, without scalar fields, and without modifications of general relativity. This demonstrates the intrinsic self-sufficiency of the S3 space as a geometric source of acceleration. Such an approach opens the way to quantum cosmology without singularities. Because S3 is compact, it has no beginning in the sense of t = 0. Its evolution can be cyclic in phase space, and the energy density never diverges to infinity. The phase dynamics delta kt represent a fractal evolution of phase. The phase curve is nonlinear, recursive, with logarithmic spiral structure. At a deeper level, this marks a transition from Riemannian to fractal spacetime geometry. For the first time since Einstein and Dirac, quantum gravity is resolved without strings or loops. The universe's acceleration is explained without dark energy. Lul acquires a purely geometric origin, and the entire process is described through phase, the intrinsic wave dynamics of space. Simply put, this is the first step toward understanding the universe as a quantum wave of S3, rather than as a cloud of matter moving through emptiness. And now I hand it over to our guests in the studio.
Welcome to the Deep Dive. Today we're looking at something really fascinating in cosmology, the whole dark energy puzzle.
Right.
We've got this theoretical paper, quantum gravity one, that takes a pretty different path. It suggests cosmic acceleration isn't some weird fluid out there.
Exactly. It argues it's more like a quantum effect. Something predictable, popping right out of the physics we think we already know.
Okay, so no mysterious dark energy field, no tweaking general relativity locally.
That's the proposal. Our mission, really, for this dive is to get our heads around how they use standard quantum gravity ideas, but, and this is key, on a specific kind of universe geometry.
Where?
A compact one. Think of space itself as being finite but unbounded, like the surface of a sphere, but in 3D. So, an S3 geometry.
A giant three-sphere universe.
Yep. And the idea is that the acceleration we see emerges naturally from the quantum stuff already present in that setup. Specifically, it hinges on this quantum mechanism known as a geometric phase.
All right, let's unpack that setup. Why the S3? Why does the universe needing to be sort of finite like that matter so much?
Well, it's crucial for making the quantum gravity calculations actually work without blowing up. When you try to quantize gravity normally, you hit these roadblocks.
The infinities.
Yeah, especially at low energies or large scales, what we call infrared or IR issues. They're messy. Using a compact space like S3 basically gives the quantum fields, like gravity waves, a finite box to live in. This makes their energy levels discrete, like notes on a guitar string instead of a continuous slide.
Okay, so it tames those infinities, makes the math like renormalization behave properly.
Exactly. It provides a kind of natural cutoff, making the quantum gravity theory more well-behaved in the infrared.
So the geometry makes the math work, and that leads to acceleration. How? Through these quantum gravity ripples. What are they?
They're the fundamental quantum excitations of space-time itself, the transverse traceless, or TT, tensor modes. You can think of them as the quantum version of gravitational waves. The paper uses a standard physics technique called a Born-Oppenheimer expansion. It's often used to separate things that happen fast from things that happen slowly.
Right.
And applying it here, they find something pretty amazing. The expansion rate of the universe, late time, the Hubble rate, HT, it turns out to be directly related to how fast a certain quantum phase difference changes over time.
Phase difference? Between what?
Between these TT modes, these gravitational wave quanta, as they evolve on that S3 background. It's a specific kind, a gauge-invariant geometric phase, sometimes called a Pancharatnam Berry phase.
Hold on, so you're saying the universe speeds up. That's the acceleration, right?
Yeah.
Because these quantum gravity waves are sort of shifting their internal quantum state, their phase, over time.
That's the core result. The Hubble rate is essentially proportional to the time derivative of this phase difference, delta theta, plus some smaller correction terms from the expansion method.
Wow. So acceleration just emerges. No new fields, no modified gravity needed locally. It's a consequence of the quantum dynamics on this compact space.
Precisely. It's an emergent phenomenon driven by the collective behavior of these quantum gravitational modes.
That's a huge theoretical leap. But how do you connect something that abstract, this quantum phase, to the things astronomers actually measure? Like, the standard dark energy parameters, 2 and 2-allers. How do you test it?
Good question. They bridge the gap using what they call a local proxy. Near today, around redshift 0 or scale factor, they match their model's behavior to the standard CPL description for dark energy.
You mean the one that looks like Dominay's 1 plus epsilon epsilon?
Exactly that form. And the really interesting part is that the parameters in that proxy, specifically the slope term epsilon times, isn't just a free parameter anymore.
No.
It gets directly predicted by the theory. It's tied to the effective energy density, or like the number of these TT modes, what they call mathcal in S and 2T.
So the amount of quantum gravitational wave stuff dictates how quickly the acceleration changes.
That's the link. More TT mode energy means a specific, predictable acceleration slope. It connects the microscopic quantum details to the macroscopic expansion history.
And they've checked this against actual cosmological data.
They have. They use a combination of recent results, things like the DSI bearing on acoustic oscillations, plus CMB data, supernovae observations, the usual suspects.
And what does it find?
Well, combining those data sets gives a value for the Hubble constant today with pretty tight error bars.
Okay, consistent with other measurements.
Yes, and importantly, the model requires that these slope parameters, epsilon and epsilon pt, must be positive. The acceleration has to be happening, and its rate can't be decreasing in this specific way. If observations ever showed otherwise, the model is immediately ruled out.
So it's falsifiable. What about that core assumption, the S3 geometry? Can we test that?
Yes, that's a key part. A compact universe like S3 should, in principle, leave detectable signatures, like patterns of matched circles in the cosmic microwave background radiation.
Have you seen those?
Not definitively. The Planck satellite data is generally consistent with not seeing them, but that doesn't kill the S3 idea entirely. It just puts limits on how small the S3 can be, or rules out certain specific configurations, like the Poincare dodecahedral version.
Okay, so the lack of detection constrains it, but doesn't eliminate it yet. And you mentioned the gravitational waves earlier, linking to the slope epsilon p theory.
Absolutely. This is another powerful test. Because the model links epsilon p to the energy in gravitational waves, any external measurement of the stochastic gravitational wave background puts limits on the acceleration slope.
Like from pulsar timing arrays.
Exactly. For instance, the nanograv 15-year data reports a certain energy density omega green. That measurement translates directly into an upper bound on how large epsilon p can be in this model. It's a direct link between gravitational wave astronomy and the dynamics of cosmic expansion.
Amazing. Any other checks?
One more crucial one: growth consistency. The expansion history derived from this model has to predict how structures like galaxy clusters grow over time. Those predictions, say for sigma Eloidae, must match what we observe, assuming standard general relativity governs gravity on those scales. Any discrepancy there would also be a problem for the model.
Right, so it has to fit the expansion and the growth of structure simultaneously.
Correct.
So, wrapping up, the central idea is pretty radical. Cosmic acceleration might not be dark energy at all, but a quantum gravitational effect, a geometric phase shift of space-time, ripples on a finite S3 universe.
That's the essence of it, and here's something to really think about. If this model holds true, the future expansion rate of our universe, this acceleration we're measuring, is directly and quantitatively tied to the background hum of gravitational waves washing over the Earth right now.
A direct testable link between the quantum jitters of space-time and the ultimate fate of the cosmos.
Exactly. A connection between the very small and the very, very large.
See you in the next one. And until then, keep thinking deeply. Subscribe to stay with us on the path. I'm Orpheus Praxis, wishing you clarity. Namaste.